Okay,
Yeah.
yes.
Yeah. Can you change your slide?
Ok, c'è il controllo.
Okay. Let's try. Okay. Well, we go to the third slide. Okay. Can it search? Okay, this one. Okay, we are talking about that the importance of chemical storage, in particular, if we can see in this slide, you can see the importance of the amount, the potential storage of different technology, and also the time of storage. For example, for lithium-ion batteries, we are in the middle of this in terms of potential of storage. And the problem is also the time of storage. We are talking about hours, but we want when we move on the upper part on the right side of this plot, we can see that hydrogen, non-synthetic natural gas, have good potential, and also the time of potential. We are talking about the order of days. This is good, in particular for the energy storage to use the surplus of energy from renewable energy. So I try to go faster to, okay. Here we can see a typical supply chain that we can organize for to combine the energy, so renewable energy, the power generated from renewable energy, connect to the electrical grid. The surplus, we can use this surplus of energy for example, produce hydrogen from water using the electrolyzer. We can stop also here our idea producing hydrogen, but the problem is one of the problem of hydrogen is storage or the transportation through pipeline. The problem is that we need to change our pipelines because it's not possible to use the actual current pipelines to transport completely hydrogen because due to the brittlement of steel. So this means that we need to change our pipelines. So the possibility is to combine the idea of renewable hydrogen, the green hydrogen, with CO2 capture in order to obviously have a possibility to transform it, for example, in methane, or also another one, methanol, for example. But for methane, it's important to take into account that we have the pipeline, we have an already existing infrastructure, we have technology for storage, and obviously it's important to say that we has also a good social acceptance, the methane. Okay, I can go. Okay, again, go in this order. As we have already seen in the previous presentation by my colleague Stefano, obviously the idea is that we can combine the green hydrogen with CO2 capture. The possibility is that if we need in general two steps. The steps for CO2 capture in general with solvent, but not only. We have seen also the potential of membranes in the previous presentations, but we need the solvent for CO2 capture. And we need the catalyst to promote the methanation, the catalytic methanation reaction. In general, can use the nickel-based catalyst that is the commercial one. And in this case, we need two different solvent, different materials, the solvent for CO2 capture and the catalyst. And for me, that works with the fluidized beds. When we have two different solids, it could be a problem in a fluidized beds because we can have problem of segregation. We can problem not a good mixing between two reactions to do two materials. So in this case, we have problem of to have good performance from our system. So to the idea to combine the two active materials, the solvent for CO2 capture and the catalyst in dual functionalities, give us also these advantages to have only in one material, so we don't have problem of mixing, for example, that we have that we can have in fluidized beds. Another potential is that we have seen this idea. We go faster with this. Okay, the other advantage is that if we have two different materials, this means also from a techno-economic point of view, in our plant we need a section for CO2 capture for example, if we implement a sorbent-based CO2 capture system, this means that we have the looping within one reactor. We have the CO2 capture that is exothermic. It is good for us, but we have also the generation step. In general, the generation step is endothermic. It's a problem. We need to supply energy, and after at the outlet of the generator, we have the CO2 stream, and we send this to the other section of the plant. We have the methanation. We have methanation step. The idea to combine dual functional material, we can combine also the two parts of the plant in only one looping. And usually we have the advantage that the two-step or the CO2 capture is exothermic, but also the methanation that is also that comes during the regeneration of the sorbent. So that is also this exothermic. Those from a thermodynamic point, from an energy point of view, we don't have problem from this point of view. In a certain way, this presentation is the following part presented by Stefano, the previous presentation, because we are going to test lithium-based dual functional material, or with the ruthenium as active phase for methanation, and sodium-based dual functional material. Okay, we see here typical condition for preparation in a flash bed. We have also seen in the previous presentation the typical activity in terms of methane production. We can see that lithium, we have a sharp production of methane with respect to sodium, and also is active at lower temperature. Okay, and the aim of the work is to test these two materials, not in fixed bed, but in interconnected flash beds. In particular, to understand what is the chemical stability over different cycles, and also the mechanical stability is an important point, in particular when you use flash beds, because we can have problem of attrition fragmentation. And also we have the possibility to have two different reactors. We have the possibility to try to change the temperature of the step for carbonation and step of methanation. Particular, okay, sorry. Okay. We have used in this work the twin beds reactor. That is a properly designed lab scale apparatus for the study of chemical looping. This consists of two flash beds. One is used for the CO2 capture as the carbonator. The second one as the methanator. We can operate these two reactors separately with different reaction environments. Particularly, we test the CO2 capture with the CO2 5% rest nitrogen at 3 different temperatures, 200, 300, 400 Celsius degree. And the methanator is for methanation step, we use the hydrogen in nitrogen, 5% or 4% of hydrogen, at 3 different temperatures. We have we have different combination temperature for methanation step of CO2 capture step. The two reactors are connected by a duct. With the utilization of ad hoc valve system, we have the possibility to transport fastly the material from one reactor to the other. So we have a realistic way to have more realistic system, considering the realistic chemical looping plant. Okay, we can see also here in this table, you can see a picture of the apparatus. We can see also here typical condition that we used for the test. In particular, for our test, we have a number of total cycles of 5. The time of the single step is 10 minutes. That give us the possibility to complete particular the methanation reaction. We use also silica scented bed materials. That is a buffer material that we use to limit the temperature fluctuation in the bed to do the reaction, but also because when we transport material from one reactor to the other, well, at different temperature, we can have fluctuation of the temperature of